It's funny how many people think of Bitcoin as this, like, static thing, set in stone back in 2009.
Yeah, like a digital fossil or something.
Exactly. But the reality is quite different, isn't it? It's been constantly tweaked, upgraded,
Oh, absolutely. More like a living technology, constantly evolving under the hood.
and that's what we're getting into today, right? This whole technical journey of Bitcoin.
Precisely. We've got some great material to draw on, looking at things like the Bitcoin improvement proposals, the BIPs. They started back in 2011.
Yeah, 2011. These are basically the design docs for changes. So our mission today, if you will, is to unpack these key upgrades.
Right, the ones that really shape Bitcoin. We're talking official BIPs, but also some, let's say, unofficial innovations and even the forks that influence things.
We want to understand why these changes happened and, what difference they actually made.
Yeah, the impacts, like on security, how many transactions it can handle, scalability, privacy, and even completely new features.
Okay, let's dive in. Maybe start with the early days, say 2012 to 2016. Feels like they were laying some important groundwork then.
Definitely. A really key one early on was BIP16, pay to script hash, or P2SH. That landed in 2012.
P2SH. What was the core idea there?
Well, it sounds a bit technical, but it was a big shift. Instead of sending Bitcoin just to a standard address like a public key, you could set it to a kind of placeholder, a hash, that represented a more complex set of rules, a script.
Placeholder for roles.
Okay.
So what did that actually enable? What new things could people do?
Huge things, actually. The most immediate impact was making multi-signature wallets much, much easier to implement and use.
So requiring like 2 out of 3 keys to spend funds, that kind of thing.
Exactly. Big security boost for shared money, but it also allowed for more complicated spending conditions generally. And importantly, it boosted privacy.
How so? Privacy.
Because you only reveal the complex script rules when the money was actually spent. Until then, all anyone saw on the blockchain was that hash, that placeholder. It looks simpler.
Gotcha. So it hid the complexity until it was needed, made Bitcoin more flexible, maybe more business friendly.
You could definitely say that. It was a step towards more sophisticated uses beyond just simple payments.
Okay, P2SH. Then also around 2012, we got BIP32, hierarchical deterministic wallets. HD wallets. Sounds user-focused.
Very much so. Before BIP32, managing Bitcoin addresses, especially if you used a new one for every transaction for privacy, was a real pain. You had to back up every single private key.
Right. Sounds messy.
HD wallets fixed that. They introduced this clever system where you could generate like a whole tree of addresses, millions of them potentially, all from one single starting point, a master seed.
The seed phrase. The 12 words or 24 words people write down.
That's the one. The actual words part was standardized soon after by BIP39 in 2013, making it user-friendly. But BIP32 provided the underlying structure.
So back up just one phrase and you backed up everything. Huge improvement for usability.
And safety. Plus easier to generate new addresses for privacy. A massive step forward for the average user.
Definitely. Okay, fast forward a bit to 2015. BIP66. Strict BER signature encoding. Sounds technical.
It is a bit technical, yeah. This one tackles something called transaction malleability.
Malleability, I remember hearing about that. That was where someone could slightly change a transaction ID without actually changing who got the money, right?
Exactly. They could alter the signature data in a way that didn't invalidate the signature itself, but it did change the transaction's unique ID, the TX ID.
And why was that a problem?
Well, it could cause chaos for systems built on Bitcoin that relied on those TX IDs staying constant. Think exchanges or more complex multi-step transactions. If the ID changed unexpectedly, things could break.
Okay. So BIP66 just tightened up the rules for how signatures had to be formatted.
Precisely. It enforced a very specific format, the DER encoding, and that largely eliminated this malleability problem. A crucial bit of housekeeping, really, for building more complex things later.
Like cleaning the pipes before you increase the water pressure. Makes sense. Then 2016, we get a cluster, BIP 68, 112, 113, relative lock time, check sequence verify, CSV. Sounds like bringing time into the equation.
You got it. These introduced more sophisticated ways to time lock transactions. We already had absolute time locks thanks to BIP65, like this transaction can't be spent until next Tuesday.
Okay.
But these new BIPs brought in relative time locks. So you could say this transaction output can only be spent, say, 100 blocks after the transaction it came from was confirmed.
So it's a delay relative to a previous event, not a fixed calendar date. What was the big application for that?
This was absolutely fundamental for Layer 2 solutions, especially the Lightning Network.
Right. Lightning needs ways to handle disputes if someone tries to cheat in payment channel, doesn't it?
Exactly. These relative time locks are the building blocks for the penalty mechanisms and the channel closing logic in Lightning. They ensure people can get their funds back safely if something goes wrong. Hugely important for scaling Bitcoin.
Okay, so those 2016 BIPs were laying crucial groundwork. Which brings us to 2017 and SegWit. BIPs 141, 143, 147. This was a big one. Contentious, too.
Oh, yeah. Segregated Witness or SegWit.
Hmm.
Probably one of the most significant upgrades Bitcoin has ever had. It did a few key things. First, it finally fixed that transaction malleability issue we talked about, the root cause of it,
How did it do that?
by essentially moving the signature data, the witness data, out of the main part of the transaction data that gets used to calculate the transaction ID.
Okay, separating the signatures.
Right. And this separation had another massive effect. It effectively increased the block capacity.
Ah, this is the block weight thing, not strictly a block size increase.
Exactly. The old 1B block size limit technically remained, but because the witness data was now sort of discounted, you could fit more transactions into that same 1B space. Effectively, it allowed for blocks that could hold closer to 2B worth of transactions, maybe more, depending on the transaction types.
Clever. So, more throughput without needing a hard fork to change the 1B rule.
Precisely. It was a really ingenious solution to a very tricky problem, navigating the whole block size debate.
And SegWit was also essential for Lightning, right? And even things popping up now, like ordinals.
Absolutely critical. Lightning became much more practical and efficient thanks to SegWit. And yeah, the way SegWit restructured blocks and allowed for more data indirectly made things like ordinals possible down the line.
Mm.
We should probably mention, too, that getting SegWit activated was quite the saga.
Yeah, I remember the debates, different activation proposals like BIP 91, user-activated soft fork UASF with BIP 148. It really showed the challenges of changing a decentralized system.
It really did. A major technical achievement, but also a major governance stress test.
Okay, so SegWit in 2017. Then things were maybe a bit quieter on the major protocol upgrade front until 2021 with Taproot. BIPs 340, 341, 342.
That's right. Taproot was the next really big one, building on SegWit in many ways. Focus was on privacy, efficiency, and making Bitcoin scripting more powerful, but also more discrete.
Discrete? How so?
Well, a key part was introducing Schnorr signatures. These replaced the older ECDSA signatures.
And Schnorr signatures are better how?
Several ways. They're more efficient to verify, which can mean lower fees eventually. And, crucially, they allow for signature aggregation.
Aggregation, like combining multiple signatures into one.
Exactly. Think of a multi-sig transaction. Instead of needing space for, say, 3 separate signatures on the blockchain with Schnorr and Taproot, you can combine them into a single signature that looks just like a regular simple transaction signature.
Whoa, okay, so that saves space, and it also improves privacy because a complex multi-sig looks the same as a simple payment.
Precisely. And that privacy aspect is enhanced further by another part of Taproot called masked Merkleized abstract syntax trees.
MAST sounds complicated.
The concept is pretty neat, actually. If you have a Bitcoin script with lots of different possible conditions for spending the money, like Alice can spend it after 6 months, or Bob and Charlie can spend it together immediately, MAST lets you hide all the conditions that weren't used.
So only the winning condition gets revealed on-chain.
You got it. All the other possibilities remain hidden. Again, more efficient use of block space and much better privacy for complex smart contract-like stuff on Bitcoin.
And this all comes together in the new transaction type, pay to Taproot or PTTR.
Right. PTTR is the magic. It makes simple payments, complex multi-sigs, and these MAS-based conditional payments all look identical on the blockchain from the outside. Big win for privacy and efficiency.
Taproot sounds like a really elegant upgrade. Okay, so we've covered the big official BIPs. What about some of these unofficial things that have made waves, like ordinals? I think you mentioned BIP 420 earlier, but it wasn't quite a formal BIP in the usual sense.
Yeah, ordinals and inscriptions are fascinating because they kind of emerge from the community, leveraging existing Bitcoin capabilities, especially Taproot. It's not a consensus change, more like a meta protocol built on top.
So what is it exactly? People are putting JPEGs on Bitcoin.
Essentially, yes. Ordinals theory assigns a unique serial number to every single Satoshi, the smallest unit of Bitcoin. And the inscription part uses transaction witness data, remember SegWit, separating that out, to attach arbitrary data, like images, text, code, whatever, to specific Satoshis.
Right, and this has caused a lot of debate. Is this using block space correctly? Is it spam? Does it drive up fees?
All of those debates, yes. It definitely sparked a huge discussion about what Bitcoin is for. Is it just money, or is it a general-purpose data layer? It's worth noting people tried stuffing data into Bitcoin before using overturn, but ordinals is, let's say, a much more data-intensive way of doing it.
And it relies on Taproot, making it easier to include that data.
Taproot's changes to scripting and witness data handling certainly made complex inscriptions more feasible and efficient than they might have been otherwise. It's a classic case of unintended consequences, maybe, or emergent use cases.
Interesting angle. Okay, another huge, unofficial, but incredibly important development is the Lightning Network. We touched on how earlier BIPs enabled it.
Right. Lightning isn't a BIP itself, it's a whole separate layer. Layer 2 built using Bitcoin's base layer capabilities. It's all about scaling.
Moving transactions off the main chain into these payment channels.
Exactly. You open a channel with someone, lock some Bitcoin in it, and then you can send potentially thousands of transactions back and forth between you instantly with super low fees. Only the channel opening and closing transactions hit the main blockchain.
Which makes things like micropayments actually viable on Bitcoin.
Absolutely. It addresses the speed and fee limitations of the base layer for everyday smaller payments. And again, things like BIP 68, CSV, those relative time locks were absolutely essential building blocks to make the whole channel mechanism secure.
It really shows how these upgrades stack up. What about colored coins? That sounds like an early precursor to things like ordinals or tokens.
It really was. This was way back pre-SegWit. Colored coins were early experiments trying to color or mark specific Bitcoins, specific outputs, really, to represent other assets. Like, this tiny fraction of a Bitcoin actually represents a share in a company or an ounce of gold.
Kind of like early tokenization.
Pretty much. It was clever, but clunky.
Right.
Hard to scale, easy to accidentally spend your colored coin as regular Bitcoin. But it showed the ambition to do more with Bitcoin early on.
Fascinating history. And there were other bits and pieces too, right? BIP 39, we mentioned the mnemonic words, BIP 174, PSBT.
Yeah, BIP 39, huge for usability. BIP 174 introduced partially signed Bitcoin transactions, PSBT. This standardized a format for transactions that aren't fully signed yet. Made it much easier and safer to do things like multi-sig, where different people need to sign, or coordinate coin joins for privacy, less passing around sensitive private keys.
Okay, improves coordination and things like Liquid or RGB.
Liquid is a sidechain, mostly used between exchanges. It's faster than the main chain, has confidential transactions, and lets exchanges issue assets pegged to Bitcoin or other things. It's federated, though, relies on a group of trusted functionaries.
So different trust model. And RGB.
RGB is newer, aiming for scalable tokens and smart contracts on Bitcoin and Lightning, but using client-side validation, meaning you verify your own stuff, keeping the data off the main chain mostly, leveraging Bitcoin for its core settlement security. Very different approach, still evolving.
Wow, okay, so the ecosystem is really diverse. Looking forward then, any interesting proposals on the horizon? You mentioned OPTAT and CTV briefly.
Yeah, there's always discussion. BIP 347, which aims to bring back an old opcode called OPCAT, could allow for more complex scripts, maybe better ways to do certain things related to ordinals, or enabling covenants ways to restrict how coins could be spent in the future. That one even got nicknamed BIP 420 for a bit, confusingly.
Okay, so more scripting power potentially. And CTV, BIP 119.
Object Template Verify, or CTV. That's another approach to covenants. It would let you create transactions that basically say, this money can only be spent in a transaction that looks exactly like this template. It could be used for secure vaults, congestion control, payment pools. Lots of potential applications are being explored.
But these aren't definite yet, still being debated.
Oh yeah. Bitcoin development is famously conservative. Changes need rigorous review, testing, and very broad consensus. It's all about balancing innovation with stability and security. That's why things move carefully.
And we saw what happens when consensus breaks down with things like Bitcoin Cash or Bitcoin SV, right? The hard forks.
Exactly. Those forks represent different visions for Bitcoin's future, particularly around scaling. They went their own way when they couldn't get consensus on the main chain. Shows the challenges and the different philosophies at play.
So wrapping this up, it's crystal clear Bitcoin isn't static. It's been this ongoing process of careful technical refinement.
Definitely. Every change, whether it's an official BIP or something bubbling up from the community, is part of this balancing act trying to improve scalability, privacy, functionality, while fiercely protecting decentralization and security.
Understanding this history, I think, really helps you grasp Bitcoin's resilience, why it's still around and kicking, and maybe where it could go.
It does, and maybe that leaves a question for you listening. Looking back at all these steps, P2SH, SegWit, Taproot, Lightning, Ordinals, Which technical change do you think has had the biggest impact so far? Or what are you most curious about seeing next in Bitcoin's evolution? It's definitely a story that's still being written.